On November 7, 1940, a steady 40-mile-per-hour wind hit the Tacoma Narrows Bridge. Not a storm, not a hurricane, just a normal breeze. Yet by late morning, the bridge was twisting 45 degrees, tearing itself apart in one of the most dramatic engineering failures ever filmed. From the day it opened, the bridge behaved strangely. Drivers felt the deck rise and fall beneath their wheels. Pedestrians felt seasick from the constant rolling motion. The locals' nickname said it all: Galloping Gertie. The problem wasn't shoddy construction. It was the design philosophy of the era. Engineers wanted long, elegant bridges with as little weight as possible. So instead of deep trusses that resist wind, they used thin plate girders, strong but extremely flexible. The bridge could carry heavy loads, but it moved dramatically under even mild wind. On that November morning, the wind hit the structure just right to trigger aeroelastic flutter, a self-amplifying vibration. When the bridge moved, it changed the airflow around it. That new airflow made the bridge move even more. Like pushing a swing at the perfect rhythm, the wind kept adding energy. The center span twisted violently, not only up and down, but rotating along its entire length. This torsional mode wasn't predicted because in 1940, engineers simply didn't have wind tunnel testing for full bridge models. They had no way to simulate these aerodynamic effects. As the oscillations intensified, stresses concentrated at the midspan. Rivets snapped, welds separated, and finally, the roadway tore apart and collapsed into Puget Sound. Amazingly, no humans died, only a dog trapped inside a stranded car. The collapse reshaped structural engineering. After Tacoma Narrows, long-span bridges required aerodynamic analysis, wind tunnel testing, and mathematical modeling to predict flutter, vortex shedding, and torsional movement. Engineers learned that bridges don't just interact with vehicles and gravity, they interact with the air itself. The lessons from this failure influenced not only future bridges, but skyscrapers, wind turbines, and even aircraft wings. The Tacoma Narrows Bridge didn't fall because it was weak. It fell because engineers were entering a world of aerodynamic forces they hadn't yet learned to respect. In engineering, and everywhere else, the forces we overlook are the ones that break us. And that is why lessons must be learned.